My name is Mackenzie Maxwell, and this is my Lab 5 Magnetic Braking with Faraday's Law. The purpose of this lab was to observe the relationship between a time-varying magnetic field to a correlated external field as related by Faraday's Law. This will be done by creating a computational model. To create this model, we will collect time data from a falling magnet through a conductive tube with aluminum foil. We will model this tube-magnet interaction computationally and then compare the computational predictions with the observed data. The real-world results of the average total time in tube was 1.534 seconds. The computational model had a measured total time in tube of 1.118 seconds. The computational model demonstrates when the forces acting on the magnet are balanced and unbalanced. These are the fundamental principles used in this law. We have Faraday's law, we have the Biot-Savart law, we have Newton's second law, which is force equals ma, and Newton's third law, where the force falling on the magnet and the force of the entire tube are equal in magnitude. This will be demonstrated in the computational model later. And we also have Lenz's law, which is around the same as Faraday's law, but it just includes that negative n. This is the experimental data from this lab. We have the initial conditions with length, the inner radius, the outer radius, the mu, which is calculated in lab 3, which is 3.8837. And we have the magnet mass and the average time, which is calculated from this data table. I have 5 trials where I measured the time it took for the magnet to fall down the tube 5 different times and took the average. These are the checkpoint questions after recording the observed data in the slide before. Why can't we use a ferrous tube, for example, a steel pipe? This is because the magnet would be attracted to the walls of the tube and would therefore not fall down the tube. This would make the time going down the tube impossible to observe. What happens to the magnet? How does it compare to the magnet falling in free space without a tube? When a magnet falls in free space, there are no overwhelming resistive forces entering the fall, only gravity is affecting it. And however, when the magnet falls through the conductive tube, it experiences a resistive force that opposes gravity, which makes it fall more slowly. This is my glow script code for the computational model. I only included the most important parts of the code, and so that as follows. I ended up changing the initial conditions to allow for my code to work with the numbers I had. I also have the calculations for R mag, R hat, and B, which is the magnetic field. So we can also, which is also the equation I have earlier on the fundamental principles. I have the calculation of the flux, and then we also have the F magnetic, and which will then move into our table, which I have, or graph I have next slide. This is the velocity versus time graph based off of my computational data or computational model code based off of the initial conditions I have on a few slides prior. We have in the very beginning a very sharp change in velocity versus time, and then at a certain point we have it level out where the forces will be balanced, and then at the end the forces will become unbalanced as it hits the stopping point out of the tube. We have a total time in tube in seconds of 1.118 seconds, which is a little bit faster than what the observed data was in the slides previously. So according to the lab protocol, the intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring. We have red versus blue, and this is the current flowing in opposite directions. Some potential errors that could have happened in this lab, which is observed by the difference in the total time it takes for the magnet to fall through the tube, could be discrepancies in the calculated mu value from lab 3, discrepancies in the accurate timing of the magnet moving through the tube, and other recognized human errors. So which color corresponds to the clockwise and counterclockwise current? Red indicates clockwise and blue indicates counterclockwise. We know this by its resistance against the increase of magnetic flux. What happens when you flip the magnet with respect to velocity and speed? There would be no change, however the directions of the current would be flipped. How does the total time in tube real world system compare? We already talked about this. It's slightly longer in the real world, and this could be based off of the human error. This could be corrected by recalculating the magnetic dipole moment or splitting the tube into more rings. How does the shape tell about the forces in the magnet? We talked about this also. There's unbalanced and balanced forces based on the timing. What would happen if the resistivity of the conductor were reduced? The induced current would have to be much larger, therefore the magnet would take much longer to fall through the tube that was observed in this lab. And if holes or slots were cut into the tube, the magnet would drop faster because the magnetic force in induced current would decrease due to the lost surface area of the tube.